All right, welcome to part 2 of Notes 8-1. I hope that you paused and reflected on what we just did. All right, explain how you could use transformations of the graph f of x equals square root x to graph g of x equals 2 square root x. Okay, so it says to explain how you could use transformations of functions. So we could, number 2, and this is on page 104. What we could do is we could graph or make a table of our parent function y equals square root x, choosing those nice values that are perfect squares. When we square root these numbers, we get these values. And then what we could do is we could make a new table and what I'm doing here is I'm multiplying my previous outputs, right? My previous outputs, I'm multiplying those by 2. So I would have 2 times 0, 2 times 1, right? These are my old outputs, 2 times 2, and 2 times 9. I'm sorry, 2 times the square root of 9, which is 3. So again, we have 2 times the square root of 0, 2 times the square root of 1, 2 times the square root of 4, and 2 times the square root of 9. And these values would be 0, 2, 4, and 6. So now, I've shown you how it happens, but in words, I could multiply each of the y values of y equals square root x by 2. And that is how I could use transformations of functions to graph my new function g of x. Number 3, consider the function f of x equals square root x and g of x equals square root 2x. Now, first let me point out that this is not the same. Would we agree? Here, I'm multiplying my y values by 2. Here, I'm multiplying inside the radical, which would be my x values. All right, write g of x as a product in the form a square root x. So it says to write g of x as a product in the form a square root x. So they want to know, how could I get this square root of 2 and make the 2 come outside of the radical? So we're on 3a. On 3a, we have g of x equals square root 2x. And they want us to write this as g of x equals a square root x. I really wish they had started us off with a perfect square. So I'm going to do a second example. H of x equals, and I'm going to put a perfect square under there, like 9. So how could I rewrite this as h of x equals a square root x? So since there's multiplication happening, all I have to do is take the square root of this number. The square root of 9 is going to pop outside. The square root of 9 times the square root of x. And the square root of 9 is 3. So this would be 3 square root x. So similarly, I'm going to do the same thing here. We're going to rewrite this as the square root of 2 times the square root of x. And the square root of 2, we already saw it was 1.41, and then square root x. So let's go ahead and write that up here. We could write this as g of x equals 1.41 square root x. All right, explain how you could use transformations of the graph f of x equals square root x, so the parent, to graph g of x equals square root 2x. So in order to do that, first, rewrite or write as g of x equals 1.41 square root x. And then next, so second, multiply each y value of the parent by 1.41. And that's how we could do that. If you want to see what that would look like, I encourage you to off to the side, right, graph this and see what you get. It'll look something similar to the previous problem on page 103 because we are scaling by a factor larger than 1. So I can say, I know that the result, when I scale this, I'm scaling by 1.41. And since this value, absolute value of A, right, is greater than 1, this will be a vertical stretch. Okay, from the parent. All right, how does this graph, g of x is equal to square root x minus 3, compare to the graph of f of x equals square root x? So we can do that in two different ways. We can do it by investigation. If we want to see what happens, we can actually look at a table of values from the parent. This is number 4 on page 103. If we want to investigate, right, f of x equals square root x, and look at our table of values, and x, and then y equals square root x, 0, 1, 2, 4, 9, and 0, 1, 2, 3. We could compare them algebraically and see what would happen if we have x and then y equals square root x minus 3 and see what will happen here. Okay, so now if I try to put in these x values of 0, 1, 4, 9 under my radical, what's going to happen here? Make your prediction. Can you see we're going to get a square root of a negative number, which won't exist on the real axis? What about if I put in 1? I'm going to get a negative square root again. Again, this won't exist. How about at 4? If I put in square root 4, if I put 4 under the radical. Well, now we're at a point where it will exist, right? Square root of 1 is 1. And the same thing will happen here at 9. So can you see the value right here where I would have gotten 0 under the radical? So what number would I have needed to put in to this radical to get 0? If you said 3, you're correct. I'm going to do that down here. If I were to put 3 under the radical, the square root of 0, which is 0. So my first point that I can graph would be when x equals 3, and I'll get a value of y equals 0. Another value would be at 4, I get positive 1. So let's look at how that would compare. I'm going to do that down here. So my parent function starts at 0, 0, and 1, 1, 4, 2, and 9, 3. But this function does not start at 0, 0. It cannot. It starts at 3, 0, 3, 0. The next value that I could graph would be 4, 1. Now, can you make a prediction based on the distance between the starting point of each of these graphs that each of these points is moving to the left 3 units? Therefore, this point would move to the left 3 units, and this point would move to the left 3 units. And my new graph would be a shift to the right 3 units. And let's make a connection between that and the behavior of what we know from the quadratic family of functions. So the family of functions, excuse me while I find that page, says that this value h will shift your graph left or right, the opposite of the sign. Was that true here? It shifted my graph to the right 3 units, which is opposite of my sign. Okay, so how does it compare? The new graph, right, g of x, is a translation. Another word for a translation is a shift to the right 3 units from f of x. It says sketch G and F from item 4 on the same axis below. So we'll do that. We're just going to copy our graph right over. So the previous graph, I hope you copied it down. Recall that the parent, I'll do that one in green. Actually, I'll do it in pink. So the parent is 0, 0, 1, 1, and then the square root of 4 would be 2, and the square root of 9 would be 3, and there's my parent, which is f of x. So this is f of x equals square root x. And then the new graph, g of x, is a translation, or whoops, a shift to the right 3 units. So this will move right 1, 2, 3. This one moves right 1, 2, 3. This one moves right 1, 2, 3. And this one moves to the right 1, 2, 3. There has been no scaling, no compressing or stretching of any kind. This would be my g of x equals square root x minus 3. So forevermore, right, we know the rule is, just like from math 2, that anything under the radical will shift your graph left or right, the opposite of the sign, that many units, h units. All right, what are the domain and range of G? So the domain for G, the domain is our x values. And remember, we've investigated this when we substituted in values, right? Some of them won't work. The earliest value that will work is 3. But we can't have a negative under the radical and get a real number. And so the domain is from 3 to infinity. So from 3 to infinity. And then this is in set notation. That's an interval notation. Set notation is x such that 3 is less than or equal to x is less than infinity. So here's set notation, set, and here's interval. The range of g of x. All right, the lowest value on the y-axis, right, on the y-axis is 0. And on the on the y-axis, the highest value, it'll keep going upward forever, so infinity. And in set notation, that would be y, such that 0 is less than or equal to y is less than infinity. All right, to check your understanding, I would like you to pause here and try these check for understandings. I'm not going to pause the video, but you need to pause here and try each of these. If you get stuck, turn on the video and I will begin giving tips on how to do these. All right, number 7, what does the graph in item 1 tell us about the relationship between the length of the boat and its hull speed? So you should look back at your graph and you should try to see the relationship between the length of the boat and the hull speed. So now, if you haven't done it, look back at your graph. And you're looking at the relationship between the length of the boat and the hull speed. I would say that as the length of the boat increases, the hull speed also increases. So number 7, as the length of the boat increases, the hull speed increases. All right, number 8, the x-intercept of the parent function, f of x equals x is 0, 0. Without using transformations, how would you find the x-intercept, also known as the square root of f of x equals x minus 3, square root x minus 3? So they want to know the x-intercept. Remember that the x-intercept is where y equals 0. So here's my y value. So I would substitute in 0 for my y value and solve for x. So I would square both sides. 0 equals x minus 3. I would add 3 to both sides, and I get x equals 3. And so my x-intercept is the point 3 for x, 0 for y. All right, let's go on to the next page, page 105. All right, page 105, describe the transformations. Oh, it says multiple transformations can be applied to the basic function, creating a new function. Transformations might include translations. Translations are shifts, right? So shift. Reflections, meaning across the x-axis. Stretching or shrinking. So we call this stretching. We always refer to it vertical stretch, so meaning it's growing upward, right? A vertical stretch. Or a vertical compression, it's growing downwards. It's a vertical compression. All right, describe the transformation of the parent function that results in the functions listed below. So what I see here, right, I see that our h value, h equals, now be careful, h is not 2. Remember, back on the previous page where we talked about transformations of functions, I think I put it in the very back, hold on, no, right here, right? H is this value right here. You notice there's a negative sign in front of it. So this negative value will always change the value of h. So for example, if I were to put in -1 for h, -1 would become +1. Or if I were to put in 7 for h, I would have negative and then +7 would look like -7. So h is always the switched sign. So h here was -2. There is no k value right here, right? No k value. And then our a value is -1. A equals -1. And again, k equals 0. So now I'm going to go ahead and write the transformation, the function, the vertex function for a square root, which is y equals a square root x minus h and then plus k. So again, h will always be under the radical, but watch your signs. Because it switches. It is the opposite sign. And then k is always the correct sign. Okay, so now it says to describe. Well, we're going to shift or translate left 2 units. Left 2 units because h is -2. And reflect across the x-axis because a is -1. All right, describe the transformation here. Here I see that a is +1. That means there's no change in a. I see that h is +3 and k is +4. So this will be a translation. So translate, right 3 units and up 4 units. All right, so sketch the graph of each function in item 9 as well as the parent function. Okay, so parent is going to be my f of x equals square root x. I'll do that in green. I'll do this one in pink, and I'll do this one in purple. And then it says use a calculator to check your results, then state the domain and range of each function. Write your answers as inequalities in set notation and interval notation. All right, so our parent, 0, 0, 1, 1, 4, 2, and 9, 3. There is my parent, f of x. Next, g of x. G of x says to shift or translate left 2 units and reflect across the x-axis. Okay, so let me refresh your memory. The order that you do these transformations in. Okay, you're always going to do them in the same order. So when we are transforming functions graphically, first, you're going to do any kind of stretching or compressing. This one won't have either. Next, you're going to reflect across the x-axis if there's a reflection. And the last move will be the translation. Okay, so that is exactly what we're going to do. We're going to stretch if there is one, reflect if there is one, and then translate if there is one. So this one, there is no stretching, but there is a reflection, so we will reflect it first. This point will reflect here. Reflecting this point across the x-axis will result in the point becoming right there. Then reflecting this one, it's 2 units above, it'll be 2 units below. This one is 3 units above, this one will be 3 units below. Now, I'm not going to darken those in because I also have to shift or translate left 2. So now this point will move to the left 2. This point will move to the left 2. This point will move to the left 2. And this point will move to the left 2. And here will be my new function, g of x. And the last one, h of x. This one, there is no scaling, right? No reflecting. So we'll start with our translation. We're going to translate right 3 and up 4. That means the parent function, right? We're going to translate it right 3, 1, 2, 3, up 4, 1, 2, 3, 4. There's the new starting point of your graph. This point will move right 3, up 4. This point will move right 3, up 4. And right 3, up 4. And there is our h of x function. Now, it does say to use a calculator to check your results. So I'll show you how to do that. You can do this in Desmos. I can do it in my graphing calculator. So I have y equals the square root of x. I have y equals negative square root x plus 2. So x plus 2. And then I have y equals the square root of x minus 3 and then plus 4. Zoom standard. There's my original function. Oh no, I shifted it the wrong way. Now, it's a good thing that I checked it. Did anybody catch that I shifted the wrong direction? If you did, kudos to you. So let's go back and fix our graph. So we're going to get rid of g of x. Do you notice I did say shift to the left 3, or sorry, the left 2, and then what did I do? I shifted to the right. This is a common error that I'll see students make. You'll identify, for example, in behavior, and then you'll write it incorrectly. So let's go back and fix our graph. So this should have been right here, right? This point, which reflected downward, should have shifted to right here. And then this point, which reflected downward, should have shifted to right here. And then similarly, this point should have shifted, this point should have shifted to right here. And our square root function, g of x, should be right here. Now, please, when you shift, be careful, use caution. These are common errors that I see students making. Okay. Next, it says to then state the domain and range for each function and write your answers in all 3 ways. I'm going to do that down here off to the side because I don't have a lot of room left. So let's match this up with the right color. So the domain for f of x, so f of x, the domain is from 0 to infinity. So from 0 less than equal to x less than infinity. Or you could say in set notation, x such that 0 is less than or equal to x is less than infinity. Whoops, bracket, my bad. And then an interval notation from 0, whoops, hard bracket, 0 to infinity. Next, for g of x. Oh, I forgot to do the range, hold on. And so for the range is going to be from 0 to infinity. So from 0 less than equal to y less than infinity. And then set notation would be y such that 0 is less than or equal to y is less than infinity. And from 0 to infinity. That's for f of x. For g of x, I think I'm going to run out of room. So for g of x, I'll try to squish it in. For the domain, 0 less than equal to x less than, oh sorry, not 0. Domain of g of x is from -2 to infinity, right? The lowest point on the x-axis is -2. So I'm going to fix that. That's -2 less than equal to x less than infinity. Underneath that, we can write it in set notation, which is -2 less than equal to x less than infinity. Oh, and I forgot my x such that, right? And in set, interval notation, it would be from -2 to infinity. My range, my range would be from the highest point on the graph, right? The highest point on the graph is 0, right? The highest point is 0. So from 0 less than equal to y less than infinity. In interval notation, that would be from 0 to infinity. And in set notation, that would be y such that 0 is less than or equal to y is less than infinity. And finally, I'll do this one up here in the purple. For this one, the domain, right? The domain is from x. X, the lowest value is 3. So the domain goes from 3 to infinity. And writing that in inequality notation and writing it in set notation. And the range, the lowest point on the graph is 4. So 4 less than equal to y less than infinity. And then in set notation, y such that 4 is less than equal to y is less than infinity. Now, let's see if we can use the structure of that to answer their question. It says, without graphing, determine the domain and range of the function. So I noticed that the domain 3 and the range 4. The domain h was 3 to infinity. The range was 4 to infinity. I noticed the same thing happened here. The domain, right, was -2. The range was 0, right, -2 and 0. And then similarly in the parent function, these are both 0. H and k are 0, and our domain and range were from starting at 0. So we can use that structure, right? If I identify h and k, h is -5 and k is -1. I can use that same structure to identify that this will shift to the left 5, so the lowest point on x will be 5. So this will shift left 5. So domain will start at 5, or begins at 5. And similarly, this shifts down 1. So range begins at -1. Okay, you're going to pause here. I'm going to pause here. You're going to try the check for understanding. Please see the